Mr. True, in this lesson we are going to learn something extremely cool. We are going to learn how to find the volume of three-dimensional objects using something called the disk method. So we're going to be able to learn how to find the volume of things that are more complicated than just like cylinders and cones. We're going to do that, or be able to do that, if we know a function which describes the outer shape of a region, and that is going to set up what we have here, a plane region. I've got a region that is bound by the x-axis, the y-axis, and this parabola is defining the outside curve of this going up to an x value of 3. Now, we're going to do this by expanding our knowledge of the first fundamental theorem of calculus, where we estimated the area of a plane region using rectangles. And we know that as we let the widths of these individual rectangles approach 0, the number of them increased until infinity, thus giving us a nearly 100% accurate estimation of the area of that plane region. Well, if we allow that to rotate around an axis, what we would get is a bunch of cylinders, and we can find the volume of a cylinder. It's pi r squared times height. And if we, again, as we reduce the widths of these cylinders, we are going to get a more and more accurate estimation of the volume. And that means that we'll be able to find questions like, well, if I had a function describing the outside of this light bulb, how much volume does it have? How much air, well actually it's in a vacuum, right? But how much volume does this glass hold? How much glass did it take to make this wine glass? Or how much does it hold inside of it, volume-wise? And this is kind of a boring example because this is just a disk of, or stack of DVDs, and it is thus a cylinder, and we can just do pi r squared times the height. But you know, we could also find the volume of all these individual disks and add them up, and thus get an estimation, in that case an exact estimation I will, of the volume of that larger cylinder that all those small little cylinders make up. So let's see here. The function is going to define the radius of each of these disks or rectangular cylinders. And delta x, if we have a horizontal axis of rotation, is going to describe the heights of those disks. Let's get this out of the way and just read formally what I've said. If a region in a plane is revolved about a line, the result is called a solid of revolution. The line is called the axis of revolution. In this case, that axis of revolution would be my x-axis, or y equals 0. The simplest region in a plane is a rectangle. Now I've covered up that diagram here, but again, the simplest region, plane region, is a rectangle, and those getting rotated around an axis is going to set up the, move my picture in a picture here. Resulting, if we rotate those, is a rectangle, which results in the simplest such solid, a right circular cylinder, which we will be calling disks. Thus, we're finding the volume, or estimating the volume of three-dimensional objects using the disk method. All right, let me get this cleared off and get to our next page of notes. Bam! Now, how do you find volume of disks when you have a whole bunch of them? Let's put this in some calculus notation. Volume of a disk is delta V is equal to pi times r squared delta x. We can see that pi r squared times height that we had back in geometry. Approximating the volume of a solid by n disks of widths delta x and radius r of x sub I. Now on the next screen I'm going to give you some nice summaries. I'm kind of building up to what we see here is our formula based off our first fundamental theorem of calculus, or using definite integration. And we'll summarize based on whether we have a horizontal axis of symmetry or vertical one. Now if we have a function in terms of x and we see a delta x here, we're talking about a horizontal axis of rotation, and these disks, if you will, are kind of vertical. So the heights of them is determined by delta x. The volume is approximately equal to the summation of where we have I starting at 1 and going up to n. This is the number of disks that we are, of course, using to estimate our volume. So we have the summation of pi, capital R, of x sub I squared times delta x. And if we want to go ahead and just go right to that using those definite integrals, allowing the delta x to approach 0, we have the limit is exactly equal to the limit as delta approaches 0, again, of pi times the summation of r of x sub I squared times delta x, where I starts at 1 and goes to n. Now, n is approaching infinity. We have a set difference here of b minus a. This would be our lower and upper limit on the x-axis if we have a, again, horizontal axis of symmetry. So we have a set difference, and if we let n go to infinity, that is going to drive the widths of all of those disks down to 0. So indeed, as we let delta approach 0, we're actually saying that we're letting n approach infinity, thus giving us an infinite number of disks and then basically an infinitely accurate estimation of the volume. The width of the largest subinterval of a partition, delta, is the norm, which is denoted by the delta surrounded by these what looks like double absolute value symbols. So we're saying that our largest partition is going to approach 0, thus all the other partitions, if they happen to be of different widths. If you remember that back when we were estimating area of a plane region using an infinite number of rectangles, well, if the largest subinterval approaches 0, then all of them are going to as well. And ultimately, we get into sort of what we're going to be using through all these examples, which is pi times the definite integral from a to b of, again, r of x sub I squared times d of x. And that's going to be pi, basically r squared times the height. All right, let's get a summary statement up here for when we have, again, that horizontal and vertical axis of revolution before we get to our first example. Horizontal axis of revolution. This side of the board kind of meets the, or matches the notation so far I've used in our video. The volume of a solid using the disk method is equal to pi times the definite integral from a to b, that's the lower value along the x-axis, and the upper value, our lower and upper limits, of r of x squared dx. And if we have a horizontal axis of rotation, then we have perpendicular representative rectangles with a width of delta x. So here is our horizontal axis of revolution, and we'll be drawing those representative rectangles, again, like I just read, vertically, and we will have a width of delta x, or d of x. So we will be integrating with respect to x, or dx. Now, if we have a vertical axis of revolution, then the volume is equal to pi times the definite integral from c to d. Our lower and upper limits, of course, are a lower and upper value of y, of r of y squared dy. Now, not only do you see that we're integrating with respect to y because we have a vertical axis of rotation as opposed to over here integrating with respect to x, but we have an r of x and an r of y. So when we want to rotate a solid around a vertical axis, we'll have to make sure that our function is x in terms of y, as opposed to over here where our function is y in terms of x. Now, and it would be a good idea to make sure, you know, like look at your picture or, you know, draw it or get it in your calculator and you know, look at that vertical axis of rotation, draw those representative rectangles, and then once you have those representative rectangles drawn, you can see, well, are my widths dy or are my widths dx, just to make sure that you're setting the problem up correctly. Now, r is the distance from the axis of rotation and the function. Our first couple of examples are going to have either the x-axis or the y-axis be the axis of rotation. So it's going to appear like we're just taking the function that is describing sort of the more irregular shape of our solid and squaring it. But our third example, I believe it is in my notes, we're going to have a solid with a hole in it. So we're going to need to remember that, you know, if, like say if this is the y-axis, then my axis of revolution is going to be x equals 0. So it's going to be the value of my function minus 0. So it's going to just seem like I'm taking my function and squaring it. But maybe if this red line is the axis of revolution, then as I rotate this plane region around, I'm going to have a hole. Well, that radius, and this is going to be a bit more of a complicated example, but you know, I would have this overall distance here, and then I would have to subtract this distance. So you will need to remember that r is not just the function describing the outside of your solid squared, it is the distance from the axis of rotation and the function. So we'll get more into that as we get to our third example. But right now, we got to get to our first one. Bang! For our first example, we are going to set up and evaluate the integral that gives the volume of a solid formed by revolving this region here about the x-axis. And before I get that started though, on the previous screen I misspoke a little bit. Our third example is going to have an axis of revolution that is not the x or y axis, but it's not going to have a hole in the solid. We're going to save that for the fourth example. So we're still going to have to take some special care into making sure that we set up that r function, that radius, correctly that we're going to be squaring in the problem. But it doesn't have to have a hole in the solid for you to need to maybe take some special care in setting up that r function. So we have a parabola opening down. We see that we have one squared term. So we have y is equal to negative x minus 3 squared plus 9. And that's this parabola here. We also have our region bound by the line y equals 0, which is the x-axis, x equals 0, which is the y-axis, and x is equal to 5. So we've got it drawn. We recognize that we have a horizontal axis of revolution, so I've drawn one representative rectangle, which is perpendicular or vertical, and we see that the width is equal to dx. So now I know that I'm just making sure that I'm going to integrate with respect to x. Thus my function needs to be y in terms of x, and it already is. You also want to make sure that you draw the picture, if the book doesn't give you one, before you go through this process of finding the volume of the solid that's being revolved around an axis. Because we don't have the issue with this one, it's the first example, but maybe that parabola, what if it had crossed through the x-axis and part of the area was below the x-axis and part of the area was above the x-axis? Well, we'd have some negative sums and some positive sums, and we would have to find the total volume of our revolved solid in two different parts, not just one. So make sure that you get those pictures drawn and you pay attention to that before you get started. We'll have that issue come up as we go through these more and more complicated examples. There's going to be a lot in this video, and you'll find them all footnoted in the description. So the volume of this solid, once we revolve it around the x-axis, is going to be found by doing pi times the definite integral from 0 to 5 of, now, our radius. Our radius is, or the heights of these rectangles are going to be found by taking the y value from our function and subtracting it with the y value from the bottom. Well, that's just going to be y equals 0, and that's why it seems like we're just taking the function and we're squaring it. But it's going to be the function minus 0, and that height is, of course, negative x minus 3 squared plus 9, and that is going to be our function giving us the radius of each disk, or again the length of each of these rectangles that are going to get revolved, squared dx. Now we've done a lot of finding definite integrals. To speed this video up a little bit, I'm going to step off and just reveal this solution and then go over them step by step. Alright, so we took the binomial and squared it. We distributed the negative and combined some like terms and ended up with 6 minus x squared. Now we can go ahead and apply that extra, or that outside power of 2. Get x to the 4th minus 12x cubed plus 36x squared dx. And just going through the power rule, we have, we're going to increase each of these powers by 1 and then divide. So increasing 4 to 5 and dividing by 5, increasing 3 to 4 and dividing by 4, and so on. And just continuing on, finishing up our process of finding the definite integral. And the volume of this plane region, rotated and draw I can't draw the three-dimensional figures for all these. That'd be not quite that good of an artist. But taking this plane region, revolving it around the x-axis, we would get a volume of 250 pi, or approximately equal to 785 cubic units. Now, what would happen if we were taking a function, I'm not going to do the same one, but taking a function and revolving it around the y-axis, thus giving us horizontal representative rectangles. Let's see what that looks like. So our second example, find the volume of a solid formed by revolving the region bound by the function y is equal to x raised to the 2/3 power. X is equal to 0, our y-axis, and y is equal to 3. And we're going to revolve that about the y-axis, or revolve it about the line x is equal to 0. So I've got it drawn. We have an intersection point here of 0, 0, and the function stays to the right of our axis of rotation through the entire, I guess if you will, the domain or the range, the values of 0 to 3. So this is just going to look a little bit different than the past example, but really not be that much more complicated. All we need to do is, because we see that we've drawn a representative rectangle perpendicular to the axis of rotation, and we have a delta y. So we're going to integrate with respect to y, which means that we need this in terms of x in terms of y, not y in terms of x. So we're going to take this equation, raise both sides of it to a power of 3 over 2, so that we can have these power to powers cancel out, giving us x is equal to y to the 3/2 power. Now the volume is going to be equal to pi times a definite integral. Our lower limit on y is 0, and our upper limit defined by the problem is 3, times r of x squared, r of x, the radius. Okay, so the radius, how long is this orange rectangle? Well, it's equal to, we're going to take we're going to plug in y and get the x values from the function, and then we're going to subtract that with, or you know, the distance is going to go from that x value back here to 0. So it's x minus 0, and x is defined by y to the 3/2 power. So it's just simply going to be y to the 3/2 power squared dy. And that means that we're going to take y to the 3/2 powers and square it. That's going to give us pi times a definite integral of 0 to 3 of y cubed dy. Then we're going to just use the power rule and integrate this and get pi times 1/4 y to the 4th power, again with those lower limits of 3 and 0. And applying that, we get pi times 1/4 times 3 to the 4th power minus 1/4 times 0 to the 4th power, of course putting in our lower and upper limits, but that's just going to be 0, so I'm just writing that for teaching purposes. And this comes out to be 3 to the 4th power is 3, 9, 27, 81 over 4 pi cubic units. And that would be the volume of this solid, bounded again by this function y is equal to x to the 2/3 power, y equals 0, and y equals 3. And that would kind of look like a funnel, if you will, coming down vertically to a point at the bottom. One last example in this part of the video where we have solids that don't have holes in them, and it will have an axis of rotation that is not an x or y axis. Third and last example of finding the volume of a solid that is created by rotating basically just one function about a line where there's no hole in it. Find the volume of a solid formed by revolving a region bounded by y is equal to the square root of x, y is equal to 0, and x is equal to 4 about the line x equals 4. Okay, well, I've got our function drawn. It's just y equals the square root of x, and the square root of 0 is 0, and the square root of 4 is equal to 2. So let's go ahead and fill that in. And as I draw my representative rectangle, which is perpendicular to the axis of rotation, I see that my rectangle is actually laying on its side. And so we are going to be integrating with respect to y, not with respect to x. So we need to take this equation and turn it around and get it y in terms of x. So that's not going to be too difficult. We have y is equal to the square root of x. We're going to square both sides and get x is equal to y squared. And that means we also need to get that, we needed that upper limit of y there. So we have, again, we have a 0 down here and a y value of 2. So we're going to be finding the definite integral between 0 and 2. And that means that the volume is going to be equal to pi times the definite integral from 0 to 2 of, well, I've kind of hinted all along, we need to put some more thought into, you know, what is this r of x, this radius? Well, my axis of rotation is way out here at x equals 4, not x equals 0 or y equals 0. So how long is this rectangle? Well, no matter how far up the y-axis I go, and my y is now my sort of independent variable, I'm going to put the y in and find x. Well, as I go up the y-axis, my largest value of x, this axis of symmetry, sort of the base of this rectangle, if you will, or the right side of this rectangle, is 4 units away. So r of x is equal to some kind of value of 4. But my rectangle doesn't go from x equals 4 all the way back to the y-axis. It stops. Well, what's this distance? Well, I'm putting in values of y, and I'm getting values of x. So this distance is y squared. So from x equals 0 to my axis of rotation, I have 4 units, and this little piece here is y squared, so the length of my rectangles are going to be 4 minus y squared. And that is my r of x. That's my function that is describing the length of each of these rectangles, or the radius of each of these discs that I'm going to use to estimate the volume. So it's going to be 4 minus y squared, yes, squared dy. And now, again, I'm doing a lot of examples. Let me just step off and reveal these solutions, or the solution one step at a time. All right, well, the workbook looks extremely similar to our previous problems. I just took this binomial, squared it, used the power rule to integrate, finished up the process of finding the definite integral, and the volume of this solid formed by taking this region and rotating it around the line x is equal to 4 comes out to approximately 53.62 cubic units. Now, so far, 3 examples have not had any holes in our solids after the revolution about the axis. But let's just say we wanted to revolve this region about the line of x equals 6. Well, we would have a hole in it. It would kind of look like a donut. So let me get this cleared off, give you a set of notes of how to approach those problems if the axis of rotation isn't really sort of one of the boundaries of our region, and finish up that example. And I'm actually going to give you 2 more. The last one's going to be quite complicated algebraically. It'll still be some polynomials, but quite the irregular shape. All right, I'm looking for the remote, but different camera, there isn't one. All right, let's get to those notes. So, as we can see in our notes here, if you get your diagram drawn, you look at the, the bound region and the axis of rotation. If you notice there's going to be a hole in that volume of revolution, then we're going to let lowercase r represent the inner radius and the capital R represent the outer radius. And then, I have this drawing set up. It's not the region that we're about to find, or the solid that we're about to find in our first, or not our first example, but our next example. But we do have a delta y, or d sub y, or d of y, because we have that vertical axis of rotation. So, if we do have a vertical axis of rotation, the volume is going to be pi times the definite integral from c to d of r of y squared minus lowercase r of y squared dy. And what you can see with each of these disks, these infinite number of disks that we're going to use to find the volume of our solid of rotation, or our solid, that we're just going to basically be finding the volume of each of these disks and then coming through and just cutting the center out with that subtraction right there. So that's what the formula looks like. Let's see what it looks like in practice. So now we have our notes out of the way. Let's get back to that previous example. Everything's going to be the same except for our axis of revolution is going to go from x equals 6 to x equals 4 to becoming x equals 6. And this time I went ahead and tried my best to draw the revolution of the solid so we can see that hole going through. Or you're starting from scratch, you draw the function, you draw the boundaries that you're trying to encompass, you put the axis of rotation and you go, oh wait a minute. The axis of rotation isn't actually part of my plane region. So again, I'm going to have that hole. Once you recognize that, don't forget the area of a solid using the disk method is pi times, with revolution, definite integral from c to d of capital R of y squared minus lowercase r y squared dy in this particular case because we have a vertical axis of rotation. So we need to figure out, all things being the same, so our lower and upper limits are still going to be 0 and 2. Remember, I just moved the axis of rotation. I can't find a disk with a hole in it. I need to find the volume of a larger disk and then subtract out the area of the inner disk. So I can't just say, well, how long is this, orange rectangle? I need to find capital R, a function that would give me capital R of y. So as I work my way again up the y-axis, my axis of rotation is x equals 6. So initially this rectangle, before we take out the center area, has to reach from x equals 6 over to wherever the function is. So it's going to be from x equals 0, 6, and then minus, I want to take out this section right here as I work my way up towards 2, and that distance is found by, well, x is equal to y squared. So that's this little piece right here, very similar to the last problem. Except before, with the axis of symmetry, or the axis of rotation, being at x equals 4, that radius was 4 minus y squared. Well, now my axis is at x equals 6, so it's 6 minus y squared. And then my inside radius, the part that we want to subtract out, well, that's just a constant difference of 2. But again, thinking about working my way up the y-axis and then seeing these distances away from where x is equal to 0 basically, how far is that? Well, that's a distance of 6, and then I want to take out this distance of 4 to give me a constant inside radius, in this particular case that we have, of 2. Now, that I have my two radiuses set up, again, from my axis of rotation, my large outside radius and my inside radius, I can finish filling up my formula here, which is going to be capital R of y, which is going to be 6 minus y squared, minus my inside radius, which is a constant value of 2 squared, dy. And now, just I'm going to step off if you want to try this on your own, but I'm going to reveal it step by step so that you can too. Alright, so I took that binomial, I squared it, I combined like terms, I went through the process of finding the integral, did the definite integral, and came up with the volume of this solid, which is equal to 192 over 5 pi cubic units, or approximately equal to 4,632.47 cubic units. If you're still watching, I got one more example. It is going to have some functions which are intersecting within the lower and upper limits of which we're trying to find the volume. So we're actually going to have to find two definite integrals or two different volumes and add them together. And that's going to be the increase of difficulty in that particular problem. If you're still watching, I certainly hope so. Bam! Bam! All right, let's get this last example finished. Find the volume of the solid generated by revolving the region bounded by the graphs of the equation y equals x squared plus 2 and y equals negative x squared plus 4x plus 8 and x equals 0 and x equals 4 about the x-axis. So that means that if we're revolving about the x-axis, we're going to have vertical representative rectangles, and we are going to, again, have a lower and upper bound on the x-axis of 0 and 4. I see that I have a parabola. Basically, this is a pretty basic one. It's just got a vertical shift of 2, so, and I'm going to draw a better sketch here in a second, but we have a parabola opening up with that 1 squared term and a positive leading coefficient. And this one's a bit more of a complicated parabola, so if I just pull this out on the side, I'm going to get that into standard form. Y minus 8, moving this over to the left, is equal to negative x squared plus 4x. You have to complete the square to get a parabola into standard form, so we're going to factor that negative out. And I'm also going to leave some space because I know that I'm going to need to complete the square. Okay, we're going to take half of that 4 and square it, so half of 4 is 2. Squared is equal to 4. And now we've added 4 to the right, but we haven't really added 4. There's a negative out front, so we actually sort of added a 4, but there is a, really it's not an addition of 4, it's a subtraction of 4. So we end up with y minus 12 is equal to negative x. Now this is a perfect square trinomial, of course, we know that. Well, there's not a power of 2 on the outside, on the inside there, but we have y minus 12 is equal to negative x minus 2 squared. So we have a parabola opening up that's got a vertex at 212 and it's opening down. Well, that means that we're going to have to find a region here bound between 0 and, well, is it bound between 0 and 4, or is there an intersection point somewhere within this interval? And actually going to give us 2 separate problems, because if these graphs intersect somewhere between 0 and 4, remember finding area bound between 2 functions. You have to do the greater function minus the lesser function, and then they swap places, or they might swap places if they intersect before we get to x equals 4. So we need to find out where these graphs intersect, and to speed up the video a little bit, I'm going to set these equations equal to each other and show the work to see if they intersect between 0 and 4. So as you can see by our algebra, we have set the equations equal to each other and got to a point where they intersect, these functions intersect at the values of 3 and negative 1. Well, 3 is the one that is the intersection value that is between our boundary of 0 and 4. So that's really all I'm concerned about. I've done a better job of drawing our sketch. And indeed, we see that our function, this downward opening parabola, negative x squared plus 4x plus 8, is the greater function, or the outside radius, from 0 to 3, and then they switch places. So we're going to have to find a volume that is created by this region rotated around the line y equals 0, or the x-axis, and then we're going to have to find another volume of this region, and that region is going to be done by seeing that our function x squared plus 2 is the outside radius, where the inside radius is the other function. So we're going to have to find 2 different volumes and add them together. So let's get this erased, and we've got volume 1, or v sub 1, is equal to the pi times the definite integral from 0 to 3 of our outside radius. Now again, our axis here is y equals 0, so it's going to be whatever value, y value we get from our outer function, or from negative x squared plus 4x plus 8 minus y equals 0. So it's going to just be that function squared. So we've got negative x squared plus 4x plus 8 squared minus that inner radius, which is going to be this function, and again we're referencing it from y equals 0, so it's going to look like it's just that function being squared. And this all, of course, integrating with respect to x, because we have a horizontal axis of rotation. So let's step out and reveal this solution in one step at a time. All right. As we saw, those graphs did intersect at that value of 3. So we have a definite integral from 0 to 3, giving us a volume after the rotation of 848.23 cubic units, approximately. And then setting up another definite integral from 3 to 4, we have another volume, which is approximately equal to 362.33, giving us a total volume of 1,210.56 cubic units. Hope all these examples help. I'm Mr. Drew. Bam! Go do your homework.